So, by now we have seen the electro-optic effect in terms of the electro-optic coefficients, the changes in the permittivity, impermeability tensor, the refractive indices, and we have categorized the effect in terms of this Pokel's effect and Carr effect, which are well known as linear electro-optic effect and quadratic electro-optic effect. Now, we will take examples of the very well known crystals. First, we will consider the electro-optic effect in isotropic media. One example of isotropic medium is the gallium arsenide, and for this gallium arsenide crystal, we will look at the index ellipsoid and under the electric field the distortion of the ellipsoid. From there, knowing the electro-optic tensor, we will try to evaluate the new refractive indices, and then we will try to look for the applications, and for that we will first estimate the birefringence and retardation. Then we will talk about the different modes of configuration of the crystal for modulator applications. Okay. So, retarder. A retarder is an optical device that produces a delay between the two orthogonally polarized light travelling in the medium. One of the polarization is faster moving, while the other is slower moving. So, as a result, in course of propagation through the medium, they will develop a path difference and hence a phase difference, and there will be a delay. This phase difference will be the, so that accounts for the birefringence and the delay. For a naturally birefringent medium, let us suppose of thickness d, the and the refractive index that is seen by the two polarizations in the direction along which the light is propagating are let us suppose designated by n x and n y, then the phase delay, that is delta phi, will be equal to twice pi by lambda n x minus n y. This is the birefringence, that is n x minus n y into d will be the phase delay between these two orthogonal polarized light. And before the electric field and after the electric field, there will be a change in the values of n x and n y. If so, then we will be able to calculate the difference n x minus n y or n y minus n x, which will be delta n x y. Then we can calculate the delay between the two polarized waves, and we will place the polarizer in such a way that both the polarizations corresponding to the refractive indices n x and n y will be excited, and if they are excited in equal amounts, then it will be a circularly polarized light. It will be orthogonal polarized light, and if the delay is such that pi by 2 phase delay, in that case it will be circularly polarized light. If the amplitudes are not different, then it will be elliptical. We have seen those examples in the earlier discussion in anisotropic medium. Okay. So, in an electro-optic medium, this retardation, that is the delay in the phase, this can be obviously controlled by the externally applied electric field, and this will result in the modulation of the light passing through the medium. So, that is the basic mechanism of modulation, light modulation by external electric field. So, for an isotropic medium, under an applied electric field may undergo changes in the refractive indices. This we have seen and we have understood very clearly that as far as there is no electric field, it is isotropic, but there may be a change in the refractive index properties when the external electric field is imposed. So, now we are going to take up an example of an isotropic medium, and we will see that the refractive index properties are modified for a certain orientation of the external electric field applied across the crystal. So, an isotropic medium may become anisotropic, showing birefringence, and because this birefringence is due to electrical field, the electric field can control the strength of the birefringence. That is, by changing the electric field, we can actually control, we can actually change the birefringence property, and hence the delay also, the delay and all other properties related to this birefringence. A half wave plate between two crossed polarizers can yield an amplitude modulator. This we have seen that if you have a variable delay element between two cross polarizers, one is polarizer at the front end and the analyzer at the back end, then by changing the delay, actually the light which is emerging out of the analyzer can be modulated, So, electrical control of retardation produces modulated light in terms of phase or amplitude that depends on the configuration, the suitable positioning of the optical elements with the optically active crystal. Okay. Now, we will refer to the list which we have shown earlier. We will focus to these isotropic elements and we will pick up this gallium arsenide, whose properties in terms of the electro-optic tensor coefficients are known, refractive indices are also known. Then we will see that how this isotropic material can become an anisotropic under certain orientation of the applied electric field. So, these isotropic crystals there are few isotropic crystals like indium arsenide, copper chloride, zinc sulphide, gallium arsenide, cadmium telluride. These crystals are used very widely for modulation in the infrared region, because these crystals gallium arsenide and cadmium telluride, they are transparent beyond this 10 micrometer wavelength. So, you have seen that for this isotropic material gallium arsenide, the 3 non-zero electro-optic tensor elements are R41, 52 and 63, but incidentally all these 3 are equal and is equal to the value of R41. So, we have this tensor which reduces to this form R41, R41 and R41, rest all other elements are 0. So, we need this tensor in terms of the values to evaluate the induced birefringence, the new refractive indices in the principal axis system, and we will use that for gallium arsenide, which is non-centrosymmetric cubic crystal. These are the non-zero elements and this is naturally isotropic, and by applying external electric field, it can create field induced birefringence. So, this is the tensor and the values are also known. We will make use of this electro-optic tensor to calculate the. So, in absence of the electric field E equal to 0, because it is an isotropic medium. So, n x, n y and n z, all of them are equal and is equal to the ordinary refractive index n 0, and the ellipsoid equation becomes a sphere given by this and represented by. So, n x, n y and n z, all of them by magnitude they are all equal. Now, in presence of the electric field, when E is not equal to 0, then you can see that the ellipse is now deformed, ellipsoid is now deformed, and the equation, new equation to represent this ellipsoid may be given by this equation, when where you can see that the other terms are also, the cross terms are also appearing in the ellipsoid equation. With the electric field, we have seen that in terms of the impermeability tensor, impermeability in presence of electric field is equal to impermeability in absence of electric field plus this focal coefficient multiplied by this electric field. So, this will give me the new impermeability tensor, but we need the change in the impermeability, that is the difference, that is n I j E minus n I j O. This difference we need, then we can calculate this quantity. So, by knowing this quantity, because electric field is known to us, the coefficients are known to us. So, we can evaluate this. If we evaluate this, then this will give me the difference, the change in the impermeability tensor. Once I have the change in the impermeability tensor, I can couple this change to the original to get the new ellipsoid, and from the new ellipsoid by diagonalization or by Euler angle rotation, we can calculate the new principal refractive indices, and from there we can calculate the birefringence, retardation and all other associated properties. That is, in a summary, the task that has to be done. So, without field, I have the form of the impermeability tensor, which are all the same diagonal elements, because it is an isotropic material. Now, in presence of the electric field, all the other off diagonal elements, they are also appearing, this and the cross terms are also appearing, because all the 6 components in general may be affected. We will see specifically which components are actually affected depending on the orientation and the property of the crystal. So, for gallium arsenide, I write the change in the this is the well known equation we have used several times before, that delta of 1 by n square, that is impermeability change, is equal to this quantity, and the explicit form is this. All the 6 elements are now evaluated in terms of this. So, this will decide who all elements will be non-zero after I take the matrix multiplication of E x, U y and E z. So, we will do that to understand this. Let us take this gallium arsenide example. So, by multiplying this with this equation, I can isolate each of the components, and you can see that delta of n square 4, that is this is non-zero, this is non-zero and this is non-zero. And interestingly, because R 41 is the only element, non-zero element, so all of them are identical, but depends on the strength of the electric field for the 3 mutually orthogonal directions. If all the 3 components of the electric fields are present, then all the 3 incremental changes in the refractive index or the corresponding impermeability will be associated as a consequence of the electric field. Therefore, the ellipsoid equation, from here we can write this ellipsoid equation, because these elements which is associated with x square, this element associated with y square, and this 3, that is 1, 2 and 3, they are all 0. That means, these square terms they remain unaffected, but there will be a coming of this cross terms, that is y z, z x and x y coming into play into the new ellipsoid equation. So, these cross terms are now associated with this new ellipsoid equation. Now, we will have to calculate the changes in the refractive indices for the new principal axis system. So, this is now the distorted ellipsoid equation, deformed ellipsoid equation. From here, we will have to calculate the changes in the refractive. Along the principal axis, the distorted index ellipsoid, we need to rotate the old coordinate axis to the new axis, and this can be performed by matrix diagonalization or Euler angle rotation, as we have mentioned earlier with the examples. That is, you can use a matrix diagonalization or you can use an Euler angle rotation to coincide the new coordinate system with the principal axis system of the crystal under the influence of the external electric field. Now, having known this equation, this where you have the effect of E x, that is electric field along x, along y and along z, all the 3 components, that is in general when the electric field is acting on the crystal in a general direction, then all the terms will be appearing, will be there. But if I consider for simplicity that electric field is applied only along a certain direction, for example, along z direction, then what happens? Because this is the way we can actually understand how this electric field is going to change the refractive index properties of the crystal. So, electric field is 0 0 1 direction, that means you have E z direction only. So, only you have this E z component, E z electric field. So, this component surviving in the ellipsoid equation, and then we can do this diagonalization of this matrix corresponding to this ellipsoid equation, or we can simply inspect that there is a cross term associated with x and y, that means it requires a rotation about z, and because x and y are symmetric, if you interchange x with y, then the equation remains invariant. So, that means the rotation about z will be 45 degree. So, that it is identical to x and y, that is 45 degree rotation. So, the new ellipsoid, so that is what just mentioned, that you require a rotation by 45 degree about the z axis, and the influence of E along x and y is identical. Okay. So, the principal dielectric axis x and y are rotated around the z axis by 45 degree, and by doing that we have seen that this through an example in the previous discussion, that it can be represented by this equation giving a Euler angle rotation. So, to understand that how we get this equation, let us look at the rotational transformation, that is the new coordinate system connected to the old coordinate system by this transformation matrix. Now, for the particular case we are discussing, we will put theta equal to 0, because that is the rotation corresponding to x and y, and phi is the rotation corresponding to z. So, then theta equal to 0, phi equal to 45 degree, we can reduce this equation to x prime equal to x plus y by root 2, y prime equal to minus x plus y by root 2 and z prime equal to z. Now, this is the transformation that is required to make the coordinate system coincide with the principal axis system of the deformed ellipsoid. But the reverse transformation is required because we have this equation in hand x, y and z. So, we have to substitute for x, y and z by x dash, y dash and z dash. So, therefore, we need a reverse transformation. X will be represented by this, y will be represented by this and z is anyway equal to z prime. Therefore, by substituting these values of x, this should be y, not y prime, this should be y. If we substitute back into this equation, we can write this equation in this form, and then it yields a set of new refractive indices, because this entire quantity is now 1 by n x square, the new refractive index for x, and this is the new refractive index for y. So, n x will be given by this, which is by binomial expansion can be approximately written as this, because this quantity is very small, 10 to the power of minus 12 or so. So, this fairly gives the value of n x, which is equal to n 0 minus n 0 cube by 2 r 41 E z. So, this is for n x, and similarly for n y we can calculate, which will be plus n 0 plus n 0 cube and so on, and n z remains n 0 itself. So, you can see that in presence of the electric field E z, the refractive index which was n 0 has now become less, depending on this r 41, whether it is positive or negative. If it is positive, it has become less from n 0, whereas n y has become more by the same amount. So, one n x has decreased and n y has increased, but n z remained the same. That means, I have a new principal refractive indices where n x is less than n 0, n y is more than n 0, but n z remains the same. So, this is how we represent the refractive indices here. So, n z equal to n 0, and this crystal cut is used as this particular cut, that when you apply an electric field along this z direction, because for an isotropic material z direction is completely arbitrary, any direction could be defined as z direction, and the result will be depending on the direction of the electric field. There we can define the x and y, if we call this is equal to z, and in the perpendicular directions, in the orthogonal directions x and y, there will be change in the refractive indices. So, if you apply an electric field along this direction, and if you inject a light to travel through the medium in this direction itself, then this light, which has two orthogonal polarization, let us suppose it has two orthogonal polarizations, will be experiencing two different refractive indices along x and y when the electric field is there, and as a result there will be a delay, there will be a birefringence depending on the length travelled by this, there will be a phase delay, and this configuration, and once you have the phase delay or the retardation, then you can set up a modulator with this. So, this configuration, that is the electric field and the light travelling in the same direction in an isotropic crystal, gives you a longitudinal modulator. So, the induced birefringence now is n x equal to this, which is less from n 0, and n y is more than n 0 by the same amount, n z equal to n 0, the original refractive indices. Hence, the birefringence, that is the difference in n x and n y, will be just this, because half of this here, half of this here. So, this will, the difference will be this quantity. So, the phase difference will be k 0 L delta n x y. So, this phase difference, you can see that is just proportional to the applied electric field strength. So, del phi is proportional to E z. So, it is this phase difference or the retardation is proportional to external field. That means that it is a variable retarder system, where the retardation can be controlled by the external electric field, that is E z. So, we have seen that because there is no other choice to talk about this isotropic system gallium arsenide, whichever direction you apply an electric field can be treated as, because it is isotropic, can be treated as E z, and then depending on this as E z, that is z direction, you will have x and y, and those x and y, the new x and y system depending on the direction of the electric field, will see the birefringence, and this birefringence can be used for modulator application, but there is no other choice apart from this when it is set as a longitudinal modulator system. So, this for this system, this retardation and light modulation can again be subdivided into two different ways of looking at it. The configuration is longitudinal, that is when the electric field and the light which has to be modulated are travelling in the same direction through the medium, then that longitudinal configuration can be designed as a phase modulator as well as an amplitude modulator, and we will see this through examples how the light can be modulated. The other way is that if you apply an electric field in the transverse direction, then you can have the phase retardation, which can again be used as a modulator. So, this configuration is also very useful when you apply the electric field across the crystal along a direction which is perpendicular to the direction of the propagation of the light waves through the crystal, and we will discuss this in the next section. So, this is the longitudinal configuration of an electro-optic modulator. You have a beam which is travelling through the medium, and you apply the electric field in the same direction, but this has some inconvenience as regards that the direction you have to put an electrode. So, usually a small hole is placed, or sometimes a transparent electrodes are mounted, so that the propagating electromagnetic wave is not obstructed. The other configuration is the transverse configuration, where the electric field is applied across the crystal and the light wave is travelling in this direction. So, these are the two different configurations, and we will discuss all in details with examples in the next section. Thank you.